Right, the next one is exercise 2. The first exercise we already solved in the previous video, and it was about finding out GCDs using Euclidean algorithm. Here also we have to apply the Euclidean algorithm, but not just to find GCDs, but going one step further and expressing the calculated GCD as a linear combination of the given integers. That is, finding these integers x and y which satisfy this equation. So here we have 4 parts. So let's see the solution. So we straight away start applying the Euclidean algorithm. We have I have the calculations with me. There's no point doing them here. So first we apply the division algorithm to divide 72 by 56. We then get 1 as the quotient and 16 as the remainder. Then in the next step we divide the divisor by the remainder, the usual process what we have in the Euclidean algorithm. So this turns out to be 3 times 16 plus 8. 8 is the remainder here. And in the next step we again divide the divisor by the remainder, and here we will have complete division, that is a 0 remainder. And there the process stops. So by the Euclidean algorithm, the last non-zero remainder is the GCD. So 8, which is 8 in this case. The greatest common divisor of 56 and 72 is 8. Now we have to find those two integers x and y, which will help us express 8 as a linear combination of 56 and 72. And in trying to find those integers, we will use these calculations. Next, and we have to use these calculations in the reverse order, starting with the penultimate one, that is not the last one of course, because it has 0 remainder, that is useless, starting from here. So 8 can be expressed in terms of 56 and 16 in this way. 8 equals 56 minus 3 times 16. Then we use this one. So when you use this one remainder 8, the first one, which is the GCD itself, has already been expressed in terms of 2 other things, and among those 2 other things, one of them is the previous remainder. Then you have to replace that with a corresponding expression. So that means we have to replace here 16. 3 times. Now in place of 16 you can write 72 minus 56. So now if you do the calculation, you ultimately get this. 56 plus 3 times 56, that means 56 times 4 plus 72 times minus 3. So x is 4 here and y is minus 3. And this linear combination equals the GCD of 56 and 72, which is 8. So if you want, you can write hence x is 4 and y is minus 3, which of course is evident, so I am not going to write it. The next one is this. Here the integers are 24 and 138. So we first go through the calculations. 138 equals 5 times 24 plus 18. Then next we divide 24 by 18. 24 equals 2 times 18 is 36, which is greater than 24, so it will be 1 times 18 plus the remainder. So it is 1 times 18 plus 6. Then in the very next step we have 0 remainder, because 6 divides 18. So by the Euclidean algorithm, and 138 is the last non-zero one. 6. Next we have 6 equal to, so we are going to use this one, 24 minus 18. Then we replace the previous remainder, 18. So this is going to be 24 minus 138 minus 5 times 24. So after simplification, this becomes 24 minus times minus 5, minus 1 times minus 5 is 5, 5 plus 1 is 6, plus 138 times minus 1. So in this case, x is 6 and y is minus 1. Then part C. In part C, the integers are 119 and 272. We have 272 equal to, in this case these are the calculations, 2 times 119 plus 34. Next you divide 119 by 34. So that gives you 3 times 34 plus 17. And in the next step, of course, you have complete division because 34 is divisible by 17. So by the Euclidean algorithm, the GCD is 17. Now again same thing. First of all, 17 equals 119 minus 3 times 34. Then we have to replace 34 with this. 272 minus 2 times 119, and that ultimately equals what? Minus 3 times minus 2 is 6, 6 plus 1 7, so 119 times 7 plus 272 times minus 3. So in this case x is 7 and y is minus 3, and there is one more which will of course be the longest. In this case the integers are 1769 and 2378. 2378, it turns out, equals 1769 plus 609. So that's the first step. In the next step, 1769 is going to be divided by 609, the first remainder, and that gives us 2 times 609 plus 551. Next, divide 609 by 551. Here I think the quotient is going to be 1, yes. I need ink. 609 equals 1 times 551 plus 58. Next, we divide 551 by 58, and that gives us, what is it, 9 times 58 plus 29, and 29, it turns out, completely divides 58. 58 equals 2 times 29 plus 0. So here the algorithm stops. So by the Euclidean algorithm, the GCD of 1769 and 2378 is 29. Now 29, first of all, 29 is 551 minus 9 times 58. Next, we replace the previous remainder, 58. So that is, replace this 58 with 609 minus 55. While doing these calculations, always remember to simplify the expression first. After replacing one remainder with an expression like this, you simplify the resulting calculation first, and then you replace the previous remainder. If you start another replacement here itself, then you will mess things up. See, I already was going to make a mistake. This is 551. Okay, so this becomes 9 plus 1, so 10 times 551 minus 9 times 609. Oh, I should not have. Okay, anyway, you have seen what the calculations are. If you want to go back to them, you can go to a previous timestamp and see what these equations were. So now we are going to replace 551, and for that we are going to use which equation? The one where 551 appears as the remainder. So I mean, it was here. I should not have wrapped that part, but anyway. So in place of 551, we can write 1769 minus 2 times 609, and outside we have 9 times 609. So this gives us 10 times 1769 minus 20 minus 9. So minus 29 times 609. Now here we need to replace finally the remainder 609 with this. So 10 times 1769 will remain as it is, because 1769 is one of the two integers of which we are finding the GCD, and minus 29 times, in place of 609 we are going to write 32378 minus 1769. So this finally gives us what? 10 minus minus becomes plus, 10 plus 29 is 39. So 1769 times 39 plus 2378 times minus 29. So in this case x is 39 and y is minus 29. So here the solution ends. Yes, 39 and minus 29. Next, exercise 3. Prove that if D is a common divisor of A and B, then T equals the GCD of A and B if and only if the GCD of A divided by D and B divided by D is equal to 1. And there is a hint also. The hint is use theorem 2.7. Let us first recall this theorem. It is that theorem which tells us that if A and B are two integers, not both of which are 0, and K is a positive integer, then the GCD of Ka and Kb equals K times the GCD of A and B. Okay, so we are being asked to use this theorem. Now, one part of this claim, you can see the claim actually is a two-way statement. Two-way statement means if this is true, you have to prove this is true, and conversely also, if this is true, you have to prove that this is true. So one implication is already a result that we have proved. So we are just simply going to mention that one, and that is this. Let first of all we assume that this is true. So let T be the GCD of A and B. Then by corollary 1 to this theorem, theorem 2,4, we have the GCD of A divided by D and B divided by D equal to 1. It has already been proved by us. Conversely, actually it's not very difficult to show this implication. There is no absolute need to appeal to this result, this corollary. You can in fact prove this quite easily. I am not going to say how. You should be able to know this by now. Conversely, let the GCD of A divided by D and B divided by D be equal to 1. And here actually we have to assume something additional, because otherwise things may not make sense. You see, let me take one example. Suppose our A is -4, B is 6, and say D is -2. Okay, then A and B are integers, not both of which are 0. So that means their GCD exists and it makes sense. And that GCD you can clearly see is actually equal to 2. However, in the exercise it's given that D is a common divisor of A and B. It has not been explicitly mentioned that D has to be positive. Here we have deliberately taken D to be negative. This is also a common divisor of A and B. Why? Because A is an integer multiple of D. A is equal to 2D. Just like that, B is also an integer multiple of B. B is equal to -3D. So D here for this particular values is just like the general case, a common divisor of A and B. What else is true? What is this? A divided by D is what? 2. B divided by D is what? -3. 2 and -3 are relatively prime. So this condition is also true. But now if we are to believe what is claimed in the exercise, then GCD of A and B should be equal to D, that is GCD of -4 and 6 should be equal to -2, which is nonsense, because greatest common divisor by its very definition is positive. So that means additionally we have to assume that D is positive. Okay, so we are now going to write that. I don't exactly remember whether we have made any convention about these integers always being positive or not. I think there is a convention in this book that if something, it's not explicitly mentioned that some variable is an integer, then we have to assume it's an integer. But I don't think positivity is also a part of that convention. It may be a negative integer also. Also, we assume that d is positive. So now d is not just a common divisor of a and b, but a positive common divisor, such that this GCD equals 1. Now we can apply this theorem. Since okay, so we can directly apply the theorem. There is no more condition. By Theorem 2.7. What is our aim now? We now have to prove that this GCD should be equal to D. We can of course write it as D times A divided by D and D times B divided by D. Note that because it's given that D is a common divisor of A and B, so A divided by D and B divided by D, both of them are integers. And because D is positive, we are able to use this theorem, because in that theorem, I already wrote the statement, right, a while back. K is positive, so that D here is playing the role of that K. So this should be equal to, you can take the D outside, times this, and this is given to be equal to 1, so you get D. And that's how you get the claim. So the additional hypothesis you have to make is that D is positive, and that's just it. So I end things here itself. There is actually no point making very long videos, because you don't tend to watch more if there is more stuff, but if it comes in short chunks which are easier to digest, then it's better. So I have reduced the length of the videos, and from now on it will be some short ones like this. If you want longer videos, please let me know. So that's just it. The next one is on Friday, and because we have already reached number theory once again, so next let us do graph theory on Friday, where we are finally going to see the notion of topological minors. So that being said, this is all for tonight. So see you on Friday with graph theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.